Welcome to the third Caribbean Mathematical Meeting. My name is Andrea Cabarcas. Let me introduce you, Mr. Geir Dahl, who comes from the University of Oslo. Professor Dahl is PhD and Master of Science of the University of Oslo. He will share with us the conference diagonal sums of doubly stochastic matrices. We will be glad to answer any questions that you may have at the end of the presentation. For this, please, you can write your answers on chat. Professor Geir Dahl, welcome. Thanks for accepting our invitation.
Thank you, Andrea, and thanks to the organizers for letting me speak. So I'm sorry I cannot speak Spanish, but I hope I can speak clearly in English so you can understand. And there are possibilities for questions afterwards. I wish I could be there. It looks like a very nice city, but maybe some time in the future it's possible. So you can see the title of my talk, which is Diagonal Sums of Doubly Stochastic Matrices. So this is some rather recent work with a colleague, Richard Buraldi. He is from the University of Wisconsin in Madison. Okay, so I will divide my talk into two parts. And the first part will be rather general. And I will be talking about this class or set of doubly stochastic matrices and recall some basic facts about these matrices from different perspectives. And then I will move on and talk about this recent research, and it concerns the notion of diagonals in a square matrix. And it has a very long term, as you can see here, which is a horrible term, but it sort of explains what's going on. Restricted constant diagonal sum of doubly stochastic matrices. So I will explain all these things in a while, but let me give you some indication. So here we see a square matrix with non-negative entries. And if you do the computations, you will see that the sum in every row is 1, and the same for every column. So the sum down here is 1, and so on. And such a matrix is called doubly stochastic. So those are the topic of this talk. And to the right, we see a 0-1 matrix, which is in fact a permutation matrix. And that means you have a single 1 in every row and column. So we'll be talking about both these type of matrices. And the specific topic is to look at so-called diagonal sums. And if you look at the ones in this matrix and the corresponding position in the matrix X, you get certain numbers. And that's called a diagonal in the matrix X. And what we want to do is to sum up those numbers and look at different diagonals and assume that these sums are equal. So that's the topic in a very broad sense. Okay, so let's start with this general part, which is on doubly stochastic matrices. And the definition is like you see. We consider real square matrices of dimension n by n, and the entries aij are non-negative. So no negative numbers in these matrices. And here it says that the sum in every row is 1. So we compute the sum in every row, it's 1, and also in every column. So all line sums are constant, they are equal to 1. If these conditions hold, the matrix is doubly stochastic. So this is a small example. So we have non-negative numbers, and the sum is 1 in every row and column. This class of matrices, I mean this set of doubly stochastic matrices, if you look at the matrices in the class that are integer valued, so all the entries are integers, then you get precisely the permutation matrices. So as we saw here, this is an example of a permutation matrix. So it's doubly stochastic and integral. So that means exactly 1, 1 in every row and column. So why are we interested in these matrices? Well, they occur in different connections, and one is in probability. So they occur in connection with random walks in probability. So if you have a so-called Markov chain on a regular graph, then the transition matrix will be doubly stochastic. Also, it's interesting from a more geometric point of view, because the set of all doubly stochastic matrices, which we denote by omega n, can be viewed as a set in the space of matrices or order n. And then it's defined by linear inequalities and linear equations, as you see on top. And that means it's a so-called bounded polyhedron. This means that it's interesting to study this set from a convexity point of view, because it's a convex set. In fact, it's a polytope, which means it's the convex hull of a finite set of points. So this set has been studied a lot in the history of mathematics from maybe the 1940s and since then. And there are lots of papers written on the subject. Okay, so I've introduced these two matrix types. So then let's mention some of the main results, a couple of main results on these matrices. And the first one goes back to 1946, where Birkhoff, who is famous for his work on lattice theory, published a paper, actually in a Latin American journal in Argentina, I think, on doubly stochastic matrices. And the same result was shown by von Neumann, actually independently, but a bit later, so he didn't know about the previous publication. So the theorem says the following, that this set of doubly stochastic matrices has certain extreme points, and those are precisely the permutation matrices. So they have a very special role. It means you cannot, extreme point means you cannot write such a point as a convex combination of other matrices. And
sorry, Geir. What means extreme points?
Yes, it means what I said now, that a point is an extreme point if it cannot be written as a convex combination of other points in the set.
Okay, okay.
So it's out on the boundary in a corner, if you like, informally. And this means that you can actually construct every doubly stochastic matrix by taking a suitable convex combination. So a convex combination is a linear combination with non-negative weights summing to 1. And you can do that from the permutation matrices. Okay, so this is this famous theorem. So these things have connections to graph theory. So actually to the theory of bipartite graphs, and in particular matching theory, which is a basic topic in graph theory. So the result above really concerns if you just change the language of a result for matching polytopes. So it can be stated in a different language in terms of matchings. It also really deals with permutations. So we have the symmetric group of all permutations, and the permutation matrices is a way to represent that group. So for instance, the permutation matrix you see here, if you look at the ones, they correspond to red edges in the bipartite graph over here. So for instance, in position row 2, column 3, you have row 2, column 3, you have an edge between those two vertices. So that edge corresponds to that one over here. So what is called perfect matchings is in a bijection to permutations and to permutation matrices. So in a way, different languages for the same object. Okay, so the essence in a combinatorial way of this is that any doubly stochastic matrix contains the pattern of a permutation matrix in its support. So pattern means the position of the non-zeros. So this provides a link to a famous result by Frobenius and Koenig, which relates the maximum size of matching in a bipartite graph and the vertex covers expressed in terms of graph language. In fact, this theorem can also be viewed as a result on matrix decompositions. So in general, matrix decomposition means that you have a matrix and you write it as a sum of other matrices that are simpler. So in fact, from the Birkhoff von Neumann theorem, we know that the doubly stochastic matrix A can be written as a convex combination, and that means such a decomposition of permutation matrices multiplied by these lambdas. In fact, matrix decompositions are often interesting subjects. So I'll just mention one such result in this connection. So if you have a square non-negative integral matrix where each row and column sum is equal to k, then you can decompose A into a sum of k permutation matrices. And in fact, these permutation matrices are disjoint in the set that the ones are in different positions. No two ones are in the same position. So this is a decomposition result. Okay. Well, much more recently, we wrote a paper on so-called alternating sign matrices, which is a generalization of permutation matrices, where we presented a number of decomposition results in case you want to take a look. Okay, I'll also mention briefly a connection to a notion of majorization. So this is a kind of order for vectors. Actually, it can be generalized to ordering matrices and functions. But let x and y be two vectors, and let x bracket j mean the jth largest component in x. Then if these inequalities hold, and the sum of all the empties are equal, so these inequalities say that the sum of the k largest components in x is no bigger than the sum of the k largest components in y. This holds for every k. If all these inequalities and this equation holds, we write x is less than y and say that x is majorized by y. This is a very important notion which has some importance in many areas of mathematics and applications. So loosely speaking, this means that x is less spread out than y, and you have a small example here. So for instance here, 4 is less than 7, 4 plus 3 is less than 7 plus 2, and the total sum is 10 in each of them. So this is the topic in a book of about 900 pages, covering the theory and applications of majorization, a very important topic. This topic connects to matrix theory in many ways. So here is a connection between this notion of majorization and doubly stochastic matrices. This is a result which goes back to Hardy, Littlewood, and Polya in a work which was the starting point of their famous book on inequalities. So it says that X is majorized by Y, as we said above, if and only if you can find a doubly stochastic matrix A such that X is A times Y. So this means that X is the image of the linear operator given by A when you apply it to the vector Y. So this connects these two areas in an operator fashion. So let me turn to the new material. So this is about this paper, which was published in Linear and Multilinear Algebra with the same title as we have on this talk. Okay. So we need this notion of partly decomposable. So we have a square matrix A, and we say that it's partly decomposable if you can permute rows and columns to get the matrix like this. So here you note that there is a zero block, and A1 and A3 are supposed to be square matrices. So below A1 you have this zero block. If this is possible, then we say A is partly decomposable. If that is not the case, we call the matrix fully indecomposable. So that's the opposite of being partly decomposable. An important fact that if A is fully indecomposable, then there exists a doubly stochastic matrix having the same pattern as A. And recall, pattern of a matrix is the positions of the non-zeros. And in fact, if you look at doubly stochastic matrices, this is even simpler in some sense, because if a doubly stochastic matrix is partly decomposable, like here, then you can permute rows and columns so that it's the direct sum of fully decomposable doubly stochastic matrices. So in other words, if this matrix was doubly stochastic, then you can prove by simple summation that all entries in A2 must be zero. So then it's a direct sum of A1 and A3. So it's, like we say in the bottom here. And the thing is that you can then basically assume that the matrices are fully decomposable. Otherwise, you can apply the theory to each of the blocks. So that's what we will do. We consider a permutation. So a permutation is denoted like this. Sigma is K1, K2, and so on. Permutation of 1 up to n. So that means the numbers 1 up to n occurs here, but in some order. That's a permutation. And we will identify a permutation with a permutation matrix. So for instance, if K1 is 5, it means that you put the 1 in column 5 in the first row. So it's defined like this: Pij is 1 if j equals ki. So the permutation gives the column numbers for each of the rows. Okay. Then let X be an n by n matrix. And then we look at the entries in X that are in the position of the ones of a permutation matrix. And that is called the diagonal of X. So that means we take out one entry for every row and every column. That is a diagonal, and we are interested in those n entries. And what we will do with those entries is to sum up. So that's called the diagonal sum, and denoted by dp of X. So here P is the permutation matrix giving the diagonal, X is the given matrix, and here you see the sum of the entries in the position of the diagonal. That's the diagonal sum. So we are interested in diagonal sums of matrices. And also we let C of X be the set of position where X has the zeros. So it's the complement of the pattern, if you like. So let's make this concrete. So here is an example with a matrix Here we have a permutation matrix. Here is the corresponding diagonal, the red numbers, and we sum these numbers up and we get a certain number, 1.99 here. In fact, we are interested in diagonals, and all of the diagonals, except those diagonals that include some of these zeros. So we look at diagonals avoiding the zeros. That's an important thing. Then a starting point of the work is some paper or some papers from the late 1970s on diagonals in matrices. And I will not state those general results, but I will state this corollary, which is what we need for this purpose. And this corollary says that if you have a doubly stochastic matrix X, and it has a specified set of zeros, so that's this set Z. So if all diagonal sums, remember diagonal sum, if all the diagonal sums that avoid Z, so they avoid the zeros, if all these diagonal sums are equal, then the matrix X is actually uniquely determined. So with this condition on all equal diagonals, there is only one matrix that satisfies this. And this is true for doubly stochastic matrices. So this uniqueness is very important. That's the starting point of this theory. And of course, usually there are lots of diagonals. So this means this condition that all diagonal sums are equal means that we actually have many sums being equal. That means we have lots of linear equations that equate these diagonal sums. Okay. Here is a simple example where there are no zeros. So this is a doubly stochastic matrix where alpha is between 0 and 1, order 2. And if you have equal diagonal sums, here is one of them, here is the other. And that means when you compute this, the only solution is alpha equal to 1/2. So here it's easy to see that there is a unique matrix. But this is just a small example. It holds in general, actually. Okay, so let A be 0, 1 matrix now, specifying this pattern we are interested in. And assume that there exists a doubly stochastic matrix X with the same pattern as A, and where all diagonals of X disjoint from C of X, all these have equal sum. So assume A has this property that such a matrix exists. Then we call this this horrible name, restricted constant diagonal sum doubly stochastic matrix. So we abbreviate that as RCDS. So here A is the pattern of this matrix. So we have the pattern, which is the 0, 1 matrix. And if all these diagonals are equal in this sense, we have this unique matrix X according to the previous result. So these are the concepts we want to study. And what we want to do is to construct RCDS, doubly stochastic matrices, and their patterns. So a basic question is, which patterns have this form that such a matrix exists? So let's give an example, which is quite easy to get. So let A be a 0, 1 matrix where you have exactly K, where K is some given positive number, exactly K ones in every row and column. Then if you define X as 1 divided by K times A, then every diagonal which is disjoint from the zeros, every such diagonal will contain n numbers and each are equal to 1/k. So then the sum is n divided by k. So clearly all the diagonal sums are equal in that case. So then X is such an RCDS doubly stochastic matrix determined by A. So that's an interesting starting example. So here you see such an example where K equals 2. So here all diagonals have sum equal to 2 actually. Okay. So one of the main results in the paper is a characterization of these matrices. So let A be a fully decomposable 0-1 matrix. Look at the row and column sums of A and assume that you have two vectors U of length n and V of length n. These are real vectors, and define a matrix obtained by entries Yij equals to Ui plus Vj. So we associate U's with the rows and V's with the columns. And in the entry, we compute the sum, but only whenever Yij is non-zero. Okay, so assume that Yij is positive whenever Aij is 1. And also assume, which is very strict, that all the row and column sums of this constructed matrix Y are equal to the same number. Okay, assume we could find these vectors in this way. Then, then X, which is the scaled version of Y by dividing by alpha, is an RCDS doubly stochastic matrix. So this first part of this theorem actually gives a kind of procedure for constructing such a matrix. Okay. The second part of the theorem says the opposite, that assuming that X is an RCDS doubly stochastic matrix, then you can construct it in precisely this way. So this is the general construction, if you like, of this class of matrices. So here is an example. Here you have the matrix A, and note that you don't have the same row and column sums. Here's row sum 3, here's row sum 2, for instance. Then let's define U like this, and V like this, and then you see the entries here are the sum. So for instance, here, this 3 is the sum of 2 and 1. So in the positions of the ones up here, we compute the sum by adding up like this. And in this case, we see that all the line sums are equal. There are 5. So therefore, by the theorem, it means that, I think I should try to move this thing here. It means that this matrix is RCDS doubly stochastic matrix. Okay.
Here.
Yeah.
Only I have a question. The last this matrix is, well, the first matrix A is symmetric, and the second matrix is always symmetric. The matrix obtained by the sum Ui plus Vj is always symmetric.
Yes, but in general, there are non-symmetric RCDS matrices. If that is your question.
The second matrix is not always symmetric, no?
No, it's not always symmetric.
Okay, okay.
Yeah. Okay, thanks. So I will do this very fast, this algorithm. Based on the first part of the theorem, you can actually, this is just a restatement of the first part of the theorem, a way to construct these RCDS matrices. It's just written a little bit differently. So the thing is, of course, that there is a difficult part here, which is to construct these vectors so that all these row and column sums are the same. But assuming you could do it, you get the matrix in this class. And also, as the theorem says, any RCDS doubly stochastic matrix may be constructed in this way. Let's give an example on this. So here we have a block matrix. So IK is the identity matrix of order K. So all these blocks are equal on top, and all the numbers on the diagonal are T. T is a given number. And below the line here, you have a matrix A. So the matrix A is of dimension n minus k times n, and it's a 0, 1 matrix. So let now ek be the vector of all ones of length k. Then we can prove the following result, that if we define some constant vectors r and s with the numbers like this, and you let A be a 0, 1 matrix with the row sum vector r and column sum vector s, this is a kind of well-studied topic, then the matrix V that we looked at above is an RCDS doubly stochastic matrix. Okay, this is a bit hard to digest all this notation, but the example here shows what's going on. So here you have the two blocks of the identity matrix, but multiplied by 2, like this. And below here we have a 0, 1 matrix with the same row sums, which is actually 4, and the same column sums, which is actually 2. And note that this class of 0, 1 matrices with given constant row sums and constant column sums, that's a huge class of matrices. So this means, as a consequence, there's a huge class here of these RCDS matrices that you can construct in this way. So the proof here uses the famous Geir-Dahl theorem, dealing with the row 0, 1 matrices with given line sums. Okay, I will now, just towards the end, say a little bit more on how we can use this result and compute things. So we can start with this 0, 1 matrix A and look at the row and column sums and construct some diagonal matrices based on these two vectors. And those numbers actually just compute the number of ones in every row and column. So then these conditional equal diagonal sums are written again down here using this notation, just saying that all the diagonal sums are equal, but we can scale so that they are all equal to 1. So this gives a linear system of equations with 2 n variables, the u's and the v's, as you remember from the theorem. So we are interested in when does this linear system, when does it have a solution? And is that solution unique? That's a basic question. So we can rewrite this system in matrix form like this. So we get a big coefficient matrix H like this, which is symmetric. And here you have these diagonal matrices, dr and ds, as I explained. And A is the by adjacency matrix of the matrix A. Well, sorry, you have the bipartite graph of A such that the bi-adjacency matrix is A, okay? So we can associate with A this bipartite graph, and then H is actually not an arbitrary matrix, but it is the signless Laplacian matrix of this graph, this bipartite graph. So the signless Laplacian actually occurs here in some a bit surprising way, I would say. But that means a lot of stuff is known about H because people from spectral graph theory know a lot of things about signless Laplacian matrices. For instance, we know that this vector E and minus C is in a null space. The matrix is positive semi-definite, it's singular. So that means that this is the coefficient matrix, and we have the right-hand side, which is the all ones vector. But we look for a solution with a certain non-negativity property. So we need this as well. So here is the linear system written in matrix form. And here you notice that the first equation is with the diagonal matrix. So this one is easy to solve like this. So remember, U and V are the unknowns here. So we can solve for U and get this expression and insert in the other equation. And we get this equation in red. So basically what we need to do to find U and V for a given matrix A is to solve this linear system given in the red here to find V. So this means essentially that we get a unique solution V, and after that, U is determined as we see above here. So the result on this is the following. So let A, you know, this given 0, 1 matrix be fully indecomposable, as we said before. Then we can, from this, prove that there exists both U and V, such that it's a solution of this system that we're interested in, equal diagonal sums. So a solution exists always, and the solution is actually unique up to a certain manner, adding a constant to each component in U and subtracting the same constant in V, because then the sum of U and V is the same. So the solution is essentially unique of this. But remember, so far it's just about the equations. We need a certain extra property. And that's what this second statement says, that A is the pattern of an RCDS doubly stochastic matrix, if and only if the U and V, as we computed uniquely above, satisfies that Ui plus Vj is positive for exactly those positions ij where A has a 1. So this is the extra condition we need. So this theorem actually answers the question, how can you determine if a matrix A is the pattern of an RCDS doubly stochastic matrix? Well, what you do is to compute U and V according to what I just said. The solution is essentially unique. And then you just check condition 2 down here. Yeah, so that's what I wanted to tell you here. And if you are interested, you may take a look at this paper with the same title in that journal from this year, actually. So these are some references, and I say thank you. And this concludes my presentation. And I hope you have maybe questions or comments.
Well, Professor, thank you so much for your participation. We have, I think, could be 7 minutes for questions. Let me check the chat. Or if you have any question, you can use the option of the raise hand of Zoom. I don't know. It seems to me there are no questions on chat. And we have no raised hand. Well, Professor Geir Dahl, has been a pleasure to hear your presentation. I thank all the audience too. We invite you to continue connected in the third Caribbean Mathematical Meeting. Muchísimas gracias, Profesor Geir Dahl, por acompañarnos, por hacer parte de esta tercera versión del encuentro. Muchísimas gracias también a todos por acompañarnos en esta primera sesión de este segundo día del tercer encuentro matemático del Caribe. Les invitamos a todos a que continuemos conectados. Thank you so much. Bye bye.
Andrea, can I just ask
Yes.
you to follow the next talk? Do I leave this link and click the other link?
Yes. Okay.
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 Okay, thank you.
Well, thank you so much. Bye bye.